We're going to pick up where we left off last time and now go through a similar construction, but this time for equations of a plane instead of equations for a line. So let's get an idea of the geometry going on here. Let's let PQ be a vector in some plane. So here, the vector PQ is contained in this plane. So say this is the point P, and we can label this again x naught, y naught, z naught. And we want the terminal point of this vector to be something that varies over the entire plane. So we can get an equation for this, for points and vectors of this form. So here's Q. We'll call this point x, y, z, since this is going to be the point that varies. And for the construction, we need a vector that is orthogonal to any vector in this plane. And so we say that the vector n is normal. So we have a vector normal to the plane. And what we mean is orthogonal to any vector PQ in this plane. And so what does it mean to be orthogonal? So we can draw a picture here. We know intuitively orthogonal just means perpendicular. So here's our normal vector n. Let's call this normal vector n given x component A, y component B, c component z here. And let's try to derive an equation for this plane. What does it mean to be orthogonal? Well, we saw in the last video, or a few videos back on the dot product, that two vectors are orthogonal if and only if their dot product is 0. So if the dot product of the normal vector with any vector in the plane is 0, well, in particular, that means the dot product of n with this vector PQ with a fixed base point P, we know this dot product should be 0. And so let's expand what it means for the dot product to be 0 here. The dot product is 0. Well, in component form, that means, well, we're writing n as ABC dot PQ, which is x minus x naught, y minus y naught, z minus z naught. And we know that this should be equal to 0 because they're orthogonal. And now we can actually compute the dot product to get a scalar equation for this plane. So if we take the dot product here, we have A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. And this is the scalar equation for a plane. I'll say for a plane containing vector PQ with normal vector n, which was given by ABC. And so we say that this is like the scalar equation. There's a scalar representation here. We can do a little bit of algebra to get this into the general form for an equation of a plane. If you notice from this scalar equation, well, that's ax minus ax naught plus by minus by naught plus cz minus cz naught equals 0. We can group all of the terms not including a variable together, and it would look like ax plus by plus cz, and then it looks like we're going to have plus, and every term that's constant or is just the product of fixed numbers, looks like it's going to be minus ax naught minus by naught minus cz naught equals 0. And so if we prescribe this entire term, this entire string of constants to be just some other letter D, well, then we have the general form for the equation of a plane. The general form is, so let's just write it on the next page here. The general form is ax plus by plus cz plus d equals 0. And then again, this is where d was equal to negative ax naught minus by naught minus cz naught. Okay, and this is the general form. So this is probably the form that you're more likely to see a plane, the equation of a plane being expressed in. And remember, the constants a, b, and c were components of the normal vector, and the constants x naught, y naught, z naught were the initial point of the vector pq that belongs to the plane. So we had normal vector, and then we had our vector PQ with base point P. And this was PQ. So now that we have an equation for a plane, let's do some examples. So let's look at this following example. Let's write an equation for the plane containing points P, which we'll say is 1, 1, -2, Q, which is 0, 2, 1, and R, which is, which is -1, -1, 0. Okay, so now the question is, what's the equation for the plane? Right? So let's look at a picture here. We have 3 points. This won't be correct, but we'll get a sketch of a picture here. So let's say these are our 3 points, P, Q, and R. And we've seen that we need a normal vector to be able to define an equation for the plane. To get a normal vector to the plane, what we can do is use the cross product to our advantage, because if you remember, what does the cross product give you? You input 2 vectors and it outputs a vector that is perpendicular to both vectors that you input. So if we put in 2 vectors that lie in this plane and take their cross product, then the result is going to be a normal vector to this plane. And so that's how we'll get our normal vector. So you get the normal vector by taking the cross product of 2 vectors in the plane. And so since we have 3 points, P, Q, and R, we can get 2 vectors, right? We can do any combination. We could do like PQ and PR. We could do RP and RQ. We could do QR and QP. The only restriction is that the 2 vectors that you take the cross product of, make sure they have the same initial point, 2 vectors. So let me interject here. 2 vectors with initial point the same. And so for us, let's do, for example, we could do PQ and PR to find our 2 vectors that lie in this plane with the same base point. You see they have the same initial point or base point by point P. And so if we take PQ, looks like we're going to have -1, 1, 3, right? So PQ is -1, 1, 3. And then similarly, PR is going to be -2, -2, +2. -2, -2, +2. And now these are our 2 vectors in the plane. We need their cross product to get us a normal vector. So the normal vector that we want is PQ cross PR. Whoops. cross PR. Okay, and so let's remember how to compute the cross product. PQ cross PR. Remember, we set up the 3x3 matrix with the first row being standard unit normal vectors I hat, j hat, and k hat. And then the second row will be our first vector, so -1, 1, 3, and then -2, -2, 2. So now we have to take the determinant of this 3x3. So let's go to the next page for a little more room here. PQ cross PR is the determinant of ijk -1, 1, 3, -2, -2, 2, which we start with I. We look then at the corresponding 2x2 submatrix, which is 1, 3, -2, 2. Take its determinant, so we get 2 minus a -6. So it looks like that's going to be, so I'll write it out. 2 minus a -6 I hat, and then alternate sign, so minus, then j hat's going to be -2 minus a -6 j hat, and then plus for k hat, it looks like we're going to get +2 minus -2. So that's 2 plus 2 k hat, which gives us the vector 8, -4, 4. This is our normal vector, right? Calculating the cross product gives you a normal vector, or a vector that's orthogonal to both input vectors. So here the input vectors were PQ and PR. And so that means this is our normal vector for the plane. And we can look back to our equation here, the scalar equation that we derived at the beginning of the video, where we just plug in that the normal vector ABC, and with base point P, which is x0, y0, z0. Or instead of having to memorize the formula, we know we can just take the normal vector and then dot x minus our point, and say we picked base point P, right? So let's use the point P, which was 1, 1, -2. So that's going to be our normal vector dot the vector x minus 1, y minus 1, z plus 2. And this should be 0 because we want that these are orthogonal. And so this then becomes the dot product 8, -4, 4, dot x minus 1, y minus 1, z plus 2 equals 0. And so now let's take the dot product. If we take the x component, we'll get 8 times x minus 1. For the y component, we have -4 times y minus 1, -4 times y minus 1. For the z component, we have 4 times z plus 2 equals 0. And here's a scalar equation for our plane that contained those 3 points, P, Q, and R. We can simplify this to general form. This becomes 8x minus 8. Looks like we'll have minus 4y plus 4 plus 4z plus 8 equals 0. And we can simplify here. We get 8x minus 4y plus 4z. And then let's see what the constant terms simplify to. Well, we have a -8 plus 8, so that cancels. And it looks like we're just left with a plus 4 equals 0. And here's the general equation. And so in general, no pun intended, this is the form you will express the equation for the plane in. You'll express it in general form. So that's how we can find the equation of a plane passing or containing 3 distinct points. Okay, so you have to have at least 3 points to be able to express the equation for the plane, right? And this time we were given P, Q, and R to be these points here. There's one other way we can express an equation for a plane, and it's based on the information given. So let's make a quick remark here. And it's about the info needed to find an equation of a plane. There's two sets of information that are sufficient. One is 3 points. 3 points in the plane. Because we could use these 3 points to come up with 2 vectors, right? And if we came up with 2 vectors, then we can take the cross product to get a normal vector, et cetera, et cetera. We end up with the equation. The other one is a point and a line. So we can have 1 point and 1 line in the plane. Using these 2 pieces of information, we can also derive an equation for the given plane. Again, it boils down to constructing 2 vectors, right? And so you could, to construct 2 vectors in a plane, you either need 3 points or 1 point and 1 line. And so now we've seen an example of how to construct an equation given 3 points. Let's do an example now, seeing how can we construct an equation for a plane given 1 point and 1 line. So this will be the second example. And let's write the equation for plane given P, which is the point 143, and L, which is the line. And we'll write this in symmetric equations. L equals, or L is given by the symmetric equations, x equals y minus 1 over 2 equals z plus 1. Right, this is a symmetric representation of a line in Cartesian coordinates. Now, we need 2 vectors, right? Because that way we can take the cross product to get a normal vector for this plane. So here's what we need. Call them V1 and V2. How can we find V1? Well, we can find V1 from the line, right? Because what do we have? Let's draw a picture of what we have. We have a line, L, and a point, P. We can pick, conveniently, we can pick a point on this line L and say, here, remember, to find an equation of a line, we need a point and a direction vector. So this line should be equipped with some direction vector. And we can say that the direction vector is V1. And then the vector V2 is just going to be whatever this point is here. Maybe I'll call this point M, say. We can get our second vector between the point M on the line and the point P that we know lives in the plane, which is, in this case, 1, 4, 3. And so this can be vector V2. And so now the question is, how do we actually find these, right? Well, we can use the equation of the line directly to get the direction vector, right? These are symmetric. So if we want to go backwards to parametric equations, we know that these are all equal to t. So we have t equals x, we have t equals y minus 1 over 2, and we have t equals z plus 1. So to go backwards now, well, the first one's easy. We have x equals t, right? The second one, solving for y, we have y equals, looks like it's going to be 2t plus 1. Then z looks like we're just going to have equals t minus 1. And how do we find this base point here, right? We're looking for this point M. How do we find this? Well, M is simply what we would get when t is 0. And when t is 0, we get the point 0, 1, negative 1, right? Because here's a plus 0. And we just take the constant terms here to get our point. Now, what about a direction vector? For the direction vector, we look at the slopes of the parametric equation. So here we look at the slopes and we have 1, 2, 1. So the direction vector for this line is 1, 2, 1. So here we found the first vector. We called this V1, right? This vector is given by 1, 2, 1 with terminal point, or excuse me, initial point 0, 1, negative 1. And if we know then that M is 0, 1, negative 1, well then we can find MP, right? So let's quickly record what we have. We have a line L. We know that M is the point 0, 1, negative 1, which is also the initial point for this vector V1, which V1 we learned is 1, 2, 1. Next, we need to find V2. And we can find V2 because we know 2 points. We can make V2 to be the vector between these 2 points. And so we let V2 be MP, which is going to be, if M is 0, 1, negative 1, and I'll record what P was 1, 4, 3, then MP is going to be 1 minus 0, 4 minus 1, and 3 plus 1. So V2 is then 1, 3, 4. So now we have V1 and we have V2. And we can take their cross product to get the normal vector. Let's look at V1 cross V2. Well, V1 cross V2 is set up by the 3 by 3 determinant I hat, j hat, k hat, 1, 2, 1, 1, 3, 4. Calculating the cross product, looks like we're going to get 8 minus 3, so 5 I hat. And minus, for j hat, it's going to be 4 minus 1, which is 3 j hat, and then plus 3 minus 2, which is just k hat. And so our normal vector, which is the cross product of V1 and V2, we calculated to be the vector 5, negative 3, 1. Right? And our last step here is to take the dot product. We know that 5, 3, negative 1 should be the dot product with x minus, and then you pick a point. Pick any point you want on the plane. And we're using M as a base point here. So let's pick M to be the point that we use. And so it's going to be x minus 0, y minus 1, z plus 1 equals 0. I'll simplify on the next page. You can see with the dot product what we would get. We'll get 5x and then plus negative 3 times y minus 1, et cetera, right? And this yields 5x minus 3 times y minus 1 plus z plus 1 equals 0. So here's the scalar equation for the plane. And we can simplify this a little more. 5x minus 3y plus z. Let's see what the constant terms add up to be. It looks like we're going to have plus 3 plus 1. So plus 4 equals 0. And here's our general equation for this plane. But this time, remember, we were given a point and a line versus in the previous example, we were given 3 points. But either way, the main goal is to construct 2 vectors and then take their cross product. And once you have the cross product vector, you just go back to our formula that since these vectors are orthogonal, their dot product should be 0. And I'd like to close this video off with one more. It's a theorem, actually, but we'll look at the picture first. If you recall in the last video, we found a formula for the distance between a point and a line. But now let's look at the distance between a point and some plane. It's not a very good looking plane. So here's our plane. And here's some point. Let's call the point P. Okay. And so from this plane, we have a normal vector, n, and let's say that the base of this normal vector is q. And so what we want is the distance here, right? But we want vertical distance. So we'll call this distance d here. We don't want this full vector here. What we want, so let's say n is longer than p. So here's our normal vector. The distance we want is the closest distance, right? And if you see here in the picture, the closer distance could be represented in blue here to some other point that may not be Q, right? Well, what is this length here? This is the distance D that we want. Notice this is just a parallel translation of the distance from Q to this projection of the vector PQ onto the normal vector. And that's exactly what this distance is. This is the magnitude of the projection vector. So this distance, so again, maybe I'll draw it in green here. With base point Q, this is the projection of the vector PQ onto the normal vector, right? And so what do we get? We get that this is the magnitude of the projection vector. Sorry, QP, right? The base point's Q. I've got it slightly backwards because we're starting at Q and ending at point P for this case. So this is a projection of QP onto N, which is, using notation we introduced, this is the absolute value of comp QPN, which is scalar projection, right? The top one is the magnitude. The magnitude of vector projection is scalar projection. And we can find a formula a little more rigorous for this if we unpack what the scalar projection is. Well, it's the absolute value of QP dot N over the magnitude of N. And so we can use this formula to calculate the distance between a point and a plane. So this is where I'd like to wrap up, talk about lines and planes from here. In the next lecture, we're going to get a little more general and have a more broad understanding of two-dimensional surfaces inside of three-dimensional space. So we'll start to look at what are called quadric surfaces. And this is any sort of surface that you can express by a handful of equations, right? Like planes. So far, we've just looked at planes, which have curvature 0, but there are very many surfaces in two-dimensional space, like spheres, cylinders, paraboloids, ellipsoids, et cetera, et cetera. And so in the next video, we'll explore a lot more general surfaces in three-dimensional space.